Hello everyone and welcome to another lesson. Today I will be continuing in the chapter 13 notes. I will be talking about enthalpy and colligative properties in terms of introducing those concepts, and then I will go over the calculations for calculating freezing point and boiling point. So to begin, when we form a solution, that happens when you mix a solute and a solvent, and the solute will dissolve in the solvent. When this happens, you actually get a change in energy, specifically heat energy. And this is essentially from bonds that are being broken and or reformed during that process of the solute dissolving. So I'm going to go over two examples here for two different situations. So let's say we have potassium iodide, which is Ki. That would be your solute. And we dissolve that in water, which is our solvent. When you do that, the container that the reaction is occurring in will actually become cold to the touch. And this is occurring because the energy or heat is being absorbed by the surrounding area. So that reaction that is occurring when the potassium iodide is mixed with the water is absorbing energy from the surrounding area. And if heat or energy is being absorbed from the surrounding area, it will make the surrounding area feel colder, so that container to feel colder. And we call this an endothermic reaction. So to illustrate this a little bit more visually, so let's say there's your container that contains water, and you add that solute, which is the potassium iodide. That will dissolve, you'll have a reaction occur, and overall, more energy is being absorbed by the reaction than what is being released. So if energy or heat is moving into the reaction from the surrounding area, you're taking heat away from the surrounding area, causing the container to feel cold to the touch. Let's look at another example in a different situation. So we have a different solute. So let's say we have sodium hydroxide, which is NaOH, and that's our solute, and we dissolve that in our solvent, which is water. In this situation, the container will actually feel warm or even hot to the touch. Now, whether or not you feel that warmth or that cold, and in terms of a really large temperature change, that just depends on how much of that substance that you added and, of course, what type of substance it is. In this situation, energy or heat is actually being released from that reaction, and we call this an exothermic reaction. So the way in which we measure how much heat overall is being absorbed is called enthalpy. So enthalpy is the net, which is the overall amount of energy, specifically heat, that is absorbed given a certain amount of the solute. It also depends on the type of solute that is in the solvent. So for that first example, when we mix the Ki, that potassium iodide, with the water, more energy was being absorbed by that reaction than what was released. This would cause the enthalpy to increase and be higher. In the other example, more energy was being released than what was absorbed overall. This would cause the enthalpy to decrease. So really, we're just looking at where is heat moving, is it being absorbed or released by that reaction, and how much energy is being released or absorbed overall by that reaction. We can represent this graphically here. So let's say we have that NaOH and that water, our solute and solvent, and we mix them together. The progression of the reaction is being shown here. So in the first step and the second step, energy is actually being absorbed by that reaction. However, in the third step, we have a lot of energy that is released to the surrounding environment, more energy than what was originally absorbed. So overall, this blue arrow right here, that would be your net amount of energy that was, in this case, released during that reaction. So overall, more energy was released than what was absorbed. So that is why this is an example of an endothermic reaction. If this was, an exothermic reaction. If this was an endothermic reaction, then this blue arrow would be going up overall, and that means more energy would have been absorbed than what was released. So that is enthalpy. We are now going to look at a similar topic, which is colligative properties. So in this case, we're going to be looking at freezing point and boiling point. So a little bit more specific than the amount of energy that's being released and or absorbed. So when we add a solute to a solvent, this will actually change the freezing point and the boiling point of the solvent itself. Now, for those two examples, let's say we have Ki or NaOH, and you add that to the water. That would actually change the freezing point and boiling point of the water. When you add a solute to a solvent, the freezing point will actually decrease. We call this freezing point depression. And the boiling point will actually increase. We call this boiling point elevation. And this change in freezing point and boiling point, it does not depend on the type of substance. So it doesn't matter if we were using potassium iodide or NaOH, the change in the freezing point and the boiling point of the water would be the same if you were using the same amounts. And how we measure the amount is through concentration. So the concentration of the solute is going to determine how much the freezing point or boiling point will change. Now, moving forward to measure concentration, we will be using little m, which is molality, not molarity. And this is calculated by finding the number of moles of the solute divided by the kilograms of the solvent. So for example, let's say we have pure water. Normally its freezing point is 0 degrees Celsius. But let's say we add a solute to that. It doesn't matter what solute it is, but let's say we added enough solute to have a 1 molal concentration. So this means that the molality is 1. It would change the freezing point by 1.86 degrees Celsius. So it would decrease the freezing point. So the freezing point of the water would now be negative 1.86 degrees Celsius. This actually explains why we put salt on our roads, because the salt, sodium chloride or NaCl, will actually decrease the freezing point of the water. So the water or the snow or ice would actually freeze at a much lower temperature. Water is freezing at negative 1.86 degrees Celsius. The freezing point and the melting point, that happens at the same temperature. So for instance, water will actually freeze at 0 degrees Celsius, but once it gets above that, then it will start melting. So if the temperature is negative 1.85 degrees Celsius, then that water would start to melt. I'm going to show you a brief clip from a video that better illustrates these concepts. And this video can be found here under videos. It's the last two. There's one that talks about how does salt melt ice. And then I'm going to show you the Professor Dave video, just a part of it. Now, some of you also might be wondering, why do we add salt to water when we are making something like pasta? A lot of people might think, this is kind of an old wives' tale, that if you add salt to water, it will make the water boil faster, which it's kind of not necessarily true. But if you're interested in reading more or learning more about that, I do have a website that this is the website right here. They actually did an experiment, does salt water boil faster? And they kind of explain it a little bit more, since there's also another concept that you have to take into account, which is specific heat, okay? I would say overall, it doesn't make your water boil faster. Most of the time, people just add salt to their water when making pasta just to add more flavor. So if you're interested in that, you can find out more. That link is in your OneNote. But back to the Professor Dave video. In this video, he talks about vapor pressure, which is a concept we will not cover, but he will talk about more so on the molecular level, what's happening in terms of the solute affecting the solvent's boiling point and freezing point.
A similar phenomenon is that of boiling point elevation. When a solution is raised to the temperature at which the solvent should boil.
So when he says boiling point elevation, that means the boiling point is increasing.
Again, there are solute particles blocking the solvent molecules from going into the gas phase. This means more heat energy.
When he says those molecules going into the gas phase, going from a liquid to a gas is when something is boiling.
Will be needed to compensate for this activity, which results in an elevated boiling point. The more solute there is, the more dramatic the effect. So the change in boiling point is given by the molality of the solution times a constant that is specific to the solvent. Freezing point depression is similar, but deals with the interface between the liquid and solid phases. For a liquid to freeze, it has to form.
So when going from liquid to solid, that is when something will freeze. He will mention a word called lattice, which that just means that crystal forming for the solid for that usually ionic compound.
A lattice. The presence of solute particles interferes with the ability of the solvent particles to efficiently form the lattice. So to compensate, the system will have to reach an even lower temperature to freeze. The equation here is similar. The change in freezing point is given by the molality of the solution times another constant. These Kb and Kf constants can be found in tables in your textbook or online.
So for the next video, I will go over these equations and how to use them to calculate the change in boiling point, the change in freezing point, and also how to calculate the new freezing point and new boiling point. In his video, he does continue and goes over examples for the math calculations in terms of using these equations. So if you feel like you need more practice, that is also available as well.